So this is part two of my record and documentation of my Gomoku AI project. This video, not probably, I will be talking about the actual network, how the neural network works, and the agent behind um, how it interfaces with the rest of my project, on how it learns and how it gets better. So in the .h file here at the very top, we have two structs here. Both of them are for just encapsulating the data needed to be able to learn and train the neural network. So the training example up here is when you have a bunch of data you want to submit for training, it encapsulates all the data needed. So a char board, so the board length is for a Gomoku game is 225, 15 by 15. So you just give it a char array of chars 225 long. You also give it the move estimate. So it tells it this is essentially a similarly sized board, a 225 length or 15 by 15 board, and each position has a potential value of if it should win or not. So let's say in the very very corner it might have a value of 0 because like if you play there you have no chance of winning. But somewhere in the center it might have a value of 0.46, which is much better than 0.0, right? So the move estimate encodes all that data in a 225 for every single position on the board. The actual board value. So given this position, well, maybe what is the likelihood a player is going to win? And this thing is between -1 and +1. So the more negative it is, the more likely player two wins, and the more positive it is, it's uh, player one wins. So the move estimate can basically gives you a board state of telling you which move is the best, uh, ir- irregardless of the board value. So the board value might say that player two is winning by a large margin. The move estimate still tells you which place on the board to move it to maybe prolong the game the longest or give you the best chance of maybe having a comeback. And obviously, just the last move made because the training does like that. And then for the other struct, training requests, it's very similar. A board length, size, which is should be just board length, but whatever. I think this sometimes I was training with tic tac toe, so I needed to encode that. The last move made, whose turn it is, and a function callback function. So this is when you're actually using the agent to create its training data. How the AlphaGo and AlphaZero algorithm works is you have the same AI playing against itself hundreds of games. Through those hundreds of games, you create all these board states. And after playing the game, you have a winner and loser, right? So using those winner and loser states, you have now a verifiable way of saying, hey, when you made these moves, it caused this result. But when you're doing those plays, when you're actually playing those games, you also need to use the AI, right? So this struct is to encapsulate a single board state for query to the neural network to get back something. And this is done asynchronously, which is why I created this callback function here. And if we look at it, all it does is it expects a torch tensor, which is a Pytorch object. There's a lot of extra stuff made in there, but essentially for people who are just playing around with it, you can treat it as mostly a n-dimensional array. It can be one-dimensional array, two-dimensional array, which is a matrix, three-dimensional array, four-dimensional, as much as you need. That's what a torch tensor is. And then a double. So the torch tensor is what's going to be called the policy. I'll get into that later. And the double is the board value, which I talked about earlier here, which is how likely, what is the current state of the board, who is winning, player one or player two. So this callback function pointer is just expecting that to come back when the neural network has done the calculations. Down here is actually the struct that contains the neural network itself, all the different layers. At first, I thought maybe PyTorch would give me an object where I can define within it what the layers look like. But no, you just what you're supposed to do is you're supposed to extend their torch module, and within the module you define which layers are within it and how they're used. So I won't go too much into the functions here, because I'll talk about them when we go to the CPP file. But what we should note is this residual net size. This is the net size to dictate how many items are in this vector. I created 4 vectors in here of batch norm 2D type layers and convolution 2D layers. And what is supposed to happen is you loop through these multiple times to create a very complex neural network. So default is 15. I think I just use the default most of the time. And yeah, and in the constructor, you basically just loop through and initialize how many of these are there. And for the default is 15 of these, and you loop through them. And that is the neural network, the actual module. Then we get onto the actual agent. And this is basically an adapter, if you know design patterns. The rest of the project uses interfaces through the network using this agent class. And it has most of the what you expect: constructor, loading and saving the model to disk. You want to train it. You want to be able to predict the value. You want to be able to predict the move. Um, and this is the actual policy and value that I'll talk about later. You want to be able to predict both, which right now is actually deprecated. I don't really use this. I just have it in here since I wrote the code, and maybe one day in the future, I may need to use it synchronously. But for the most part, I use this predict both async that I wrote so that I can do everything asynchronously, which is way more efficient once you know how the Pytorch library works. And the get model path is just something for disk. Is where is the disk? Where is the model saved on disk? Process queue send GPU. This is just asynchronous stuff. Create tensor board is a helper function to turn these char star arrays into a torch tensor that is perfectly made to be fed into the neural networks that we created up here. Um, there's a specific format that you have to fit for a torch tensor for these kind of depending on how you construct it. And if you don't, you run into so many compile problems. I ran into many when I was making this project originally. Train GPU async. This is when you actually start training it, and everything else is member variables. This is the network shared pointer to the net, which I showed above. Training request. This is a queue. Yeah, this entire block here is just for the asynchronous part, which I'll get into. You can see I have mutexes. I have a reference to the end of the queue. And 2 threads. String model path is the path to disk, and a shutdown, which is also to help with asynchronously. So that is the .h file. Let's move over to the main meat of this video, which is the CPP file. You'll see up here I have a bunch of macros defined. Batch size and batch queue size are both 64. These are used to basically size the appropriate amount of training requests being sent to the GPU. At the time I wrote this project, I had a GTX 970 with 3.5 gigs of DDR5, GDDR5 memory, and another 500 megabytes of something else. In those experiments, I found that with the size of my neural network, 64 kind of hit the sweet spot. So yeah, 64 is what I use here. And then convolution 2D filter size is basically how many how many nodes are in the hidden layers of my neural network. And you can see that being used quite extensively here in the constructor, which is a good segue to the constructor of the neural net. So in the neural net, the constructor is extremely simple here. It just calls the actual private function CTOR after setting the residual net size. So obviously most of the work is done in here. And honestly, most of the work is just initialization. You can see here, I'm just registering the model of an N1 and then giving it a newly created convolution 2D layer with its convolution 2D option parameter. And this is where you can hit into a lot of problems if you're just starting up using PyTorch++. these convolution 2D options aren't exactly clear on how they interact with the shape of an incoming tensor. So from my experience, it really depends on how you view multidimensional arrays. But I'll talk about that a little bit later. But for now, I'll just say that all this is just initializing. I can reserve the size of my vectors, and then you can see here I loop through it, and then I just register all of them with newly created neural network layers with the exact size here, and then I do a bunch of more initialization. So all of this is just honestly just object creation. Now, for what it means to use these convolution 2D options, this 4 here does not mean the actual number of inputs you're putting in. So you would expect that if I have a 15 by 15 board that I encode it into char star char 225, that this thing should be 225. No, this is actually a 1, which messes a lot of people. Well, I don't know if it'll mess a lot of people up, but it messed me up a lot when I first started. So this is actually just the size of the first dimension. If you put 225, 225, or let's say let's say it a little bit better, 15, 15. This is actually 15 because it is the size of this thing here. If you try to move it back, so let's say it's 15 here, but you have 3 15 by 15s. This thing is now 3. And that messed me up so much. Well, I just didn't understand it. But for the first input, it's actually the size of your first dimension in your torch tensor. Once you understand that, it makes understanding how to use these convolution 2D or how you construct them a lot clearer. And what it also does is makes it so that you don't need to think about too much afterwards, because afterwards you can just use this one macro for how you construct it, and it all just kind of works. It just all kind of just magically works. So the input is going to be how many first order dimensions you have. This is the output of how many items this neural net is going to be outputting to. And then because I have it as a set size, the batch norm only takes in one size. It has a 1-to-1, so it takes in one size and outputs the exact same size. So you only give it one number, and it kind of works here. This last number is a kernel, and if you know anything about how graphics does filtering, so let's say for anti-aliasing, right? What it does is uses a smaller array to do a filter on the larger array. So let's say I have a 1020. Let's just go with our board, actually. 225 and 225 array. What you can do is you can have a 3 by 3 array, right? And this thing will then go to every single square, on this 225 by 225 array, and every single square it'll do some kind of filter. And then and if you know anything about graphics filter, the center spot is at the point that you're trying to filter, and it uses like a window to all its neighboring numbers, and it does a calculation, some kind of equation on all the numbers within this window, sums it up together, does some more equations, and the resulting number they put back into the center of the window. And this thing here is just detailing how big the window is. So for here, it is a 3 by 3 window. Okay. So convolution 2D takes in 4 dimensions, or 4 first order dimensional array, outputs to whatever number you set here with a kernel size of 3, which is the window size. The batch norm takes in your output size and outputs it the same. And you can see here convolution 2D, it matches with the batch norm that when a batch norm comes out, it is in the first order of the same. So you need to put the first order here, and outputs the same, kernel's 3, and all just works. In the policy here, you can see that my convolution 2D this time gets out, takes in 225, or 128, sorry, 128, but then it outputs to 4. So this is a 4 item, which is why this batch norm here needs to take in 4, which will output 4 again. And the linear is takes out 4 first order dimensions, and linear takes every single item and kind of outputs it into 1 board length. So you can see here there's 4 times the board length, because when it came into here, the 4 dimension was of board length, and I transform it into 1 board length. So it kind of, I don't know what linear does, but it turns 4 essentially this 4 225 into a 225. It does some math to that. The linear kind of explains to me it's probably some kind of linear regression algorithm, but yeah, that's essentially what it's doing. And the value here, you can see it takes in that 228 and puts it into 2 dimensions. This batch norm takes 2, and same thing, you do a linear of 2 to 64, and then I do one more 64 to 1. And this is just a gradual regression of the layers into one single value. And this is a good point to transition into why I have a policy and a value. I talked before about how you have a board detailing which place that you want is most likely to give you the best result, and a overall value for the entire board. This is because in the AlphaGo / AlphaZero algorithm, they found that for it to be able to learn properly and quickly, having both these numbers is actually quite helpful. So I could use the same neural network to and then which is the basis of which is up here. You can see here I have a convolution network and batch norm, and then like 15 layers of 4 different neural network layers. So 15 like blocks of this stuff. That's like the basis, and that is the complete foundation of it. And then from the output of that, I have a couple more simple mini neural networks that turns that information into a policy and a value. The policy here then, forward policy, what it does is it runs through the entire neural network here to run through the foundation, and then at the end here runs through the policy neural layers to output a grid, a 15 by 15 grid, or 225 long, to represent every single position's likelihood that you'll win. So 0, 0 might have a value of 0, but in location or row and column of 7, 6 might have a very good number. It's like 0.3, 0.4, something like that. This is what the forward policy does. It runs the foundation and gives you a entire 225 sized grid, telling you which location it thinks is the best. And in how it should operate is it gives you the highest number. You're looking for the highest number from this output. For value then is you run the foundation and you give it the value neural layers, and it will output basically just one single float / double, which is just how good or what is the current state of the board. Is it player 1 favored or player 2 favored? So that's all this is doing, is just actually running through it. So you can see here forward X, you give it a tensor, which is going to be like the encoded state of the board in a torch tensor form. You give it to the convolution N1, which outputs another torch tensor, which you forward to the batch norm, which you store in the tensor, and you kind of just keep feeding it forward, 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 and kind of just feed it through. There's a bunch of ReLU um, layers here, and I don't remember what ReLU is. You can Google it, but I'm pretty sure it's when like if it's below a certain amount, it auto puts it to 0. But if it's this above a certain amount, it keeps it there. So that's probably what ReLU does. Yeah. So that's forward value and forward policy, and that's how basically the entire neural network works. Obviously, there's forward both, which you can have the foundation, and you actually run the policy and value separately. There is a little bit of copy code, which I probably should fix, but it's not too big of a deal right now. Train here is just a helper function. Um, the batch norm neural network layers need to be primed to be either in evaluation mode or train mode. So train is on, and if you look down here, I also have eval. So this is putting into evaluation mode. This is putting onto train mode. Convolution 2D layers don't need to do this. So this is all this here just to help me quickly go through and get set everything to be primed for training. Okay, we can now move on to the agent. The agent constructor, pretty simple. You construct the network above. This block here is just loading it from file if you can. The network, this line is to prime the network to work on the GPU instead of the CPU. By default, it goes to the CPU. Already talked about the evaluation. And this is the asynchronous code. So I allocate using C-style malloc a queue of the batch queue size, which I set to 64. I never want to have a queue size batch of bigger than 64, so I just malloc 64 times my training requests in the heap. And the worker thread is starts up, and it's basically going to be a infinite loop that just keeps working until the system stops. So let's just go to the process. Actually, we can go to the destructor first instead of the process queue. The structure is pretty simple. This line here is something you should do on your graphics card to flush all the memory. I don't remember why you need to do it. I just remember that you should do it because sometimes memory can linger on the GPU VRAM, even though the process has exited on the CPU. Because the CPU works with system memory, right? RAM, and the VRAM is technically something different. This call basically tells the GPU to flush its memory. So sure. And freeing up the malloc, good coding practice, and joining or ending the worker threads if that they are spinning. So that's fine. So let's go to the process queue. Actually, no, we shouldn't do the process queue. We need to do the wait, where is it? Train both. Oh, train both async, predict both async. Here it is. So for the actual asynchronous part, I want to talk about this because to me it's pretty well good engineering. The rest of the project doesn't directly access the neural network and tell it to train weight in a synchronous manner. What it does is it requests it, and on a high level, what this agent does, it puts it onto the queue, which is what you can see here, and then exits out the function. The rest of the project then is just waiting for this function to be called back. So it can continue playing some other games, but eventually it's doing is waiting for this callback function to be called. So how this works then is I create a lock and then go into a spinning loop. This spinning loop, all it does, it checks if there's size in the queue. Remember, I have a request end reference to the end of the queue, and if there is like 64, oh yeah, I incremented. So if there's like 64, which means it's the end of the queue, then I don't have room, so I should wait for 2 milliseconds. It'll spin back around. It'll and you'll notice here that I'm locking. When I'm reading it, this is so that when I am thread safe, I lock the lock, I read it. If I can't use it, I delete the guard, which means I release the lock and I sleep for 2 milliseconds. But if I haven't, if I do have room, I break out of this loop while still holding on to the mutex. I copy all the data into the request queue and I increment the uh, end pointer. Only then do I delete the mutex because I have this thing is asynchronously assigned, so you need to have thread safety. So this format makes sure that I have thread safety. And this is just loading up the queue. And then I have a process queue here. This thing, this is for initialization. When it's initializing, obviously you don't have any games generated yet. So I just have it waiting 10 seconds to populate the queue a little bit. And once that's done, this is the main thing. And you can see here, while shutdown is not true. So this is a completely infinite loop. All it does, it goes through this whole block and then comes back up again. There's no sleeps other than if the queue is empty. If the queue is empty, we wait 10 microseconds and then figure out if you need to come back. But what it does in one go is figures out how many items are in the queue. This is this scope right here. And you'll notice I make a scope lock because in this part, it's a critical section where you get how many items are in the queue. You copy it into a local copy. So you can malloc here the size of the queue, the training, and then you just you malloc it, and then you mem copy the entire thing over. You set the request endpointer to 0 and you exit it. So now the request queue is empty. I didn't zero it out. I just set it I just set the endpoint to the beginning so so people can just overwrite it easily. And now I can work completely with this queue copy. So with this queue copy, what I do then is uh, I create tensor boards. You can see here, I just go through the entire queue copy loop and basically create tensor board from all the information that was encoded in there. These are just for declares to make sure I have the right shape. You can queue size, which is how many there are. Callbacks. So the callbacks is this when you called predict both async, you give it a callback, right? Which was stored in this training request. When you're actually processing queue, I put the callback in the same index, as the batch input tensor, right? I'm making this is a little bit flaky, but essentially what it's doing is the fourth item of the batch input tensor should associate with the fourth item in the callbacks. And once we have this full batch input tensor, I can then finally move it to the GPU. Obviously, I wait for the GPU thread to finish, but once it's finished, I know the GPU thread is free. I can send it to the GPU thread and can come back and start loading up the memory and start working on it again. The reason why I want to do this is this thing can wait for a little. Loading it into GPU takes time, which could be used to load memory. But while the GPU is working, I don't want to load more stuff into the queue. So all this works in a kind of good way. While it's waiting for the current GPU thread is finishing up its current requests, the rest of the project is making predict both requests and put it into the request queue. The second the thing is done, I can then come into here, send it to the GPU, quickly free up the queue copy, and start copying it again while the GPU is working. So the GPU is going to be the main bottleneck here, but the actual code to send to GPU is extremely simple. You just have it call for both on the input tensor. That's it. These are outputs. The for both call gives it an input tensor, and then these policy value is going to be its output. And do the exponential because softmax takes the logarithm. So the value that the rest of the project I found for me that likes it in the exponential form, which is like the normal value. So I take the exponential, I pass it out, and here the callbacks. You can note here the policy I and the value I have the association with the proper indexes, and just callbacks. And this thing can be slow. This thing can take up to like 20, 40, maybe even 100 milliseconds. It's actually quite slow in computer time. This is why it's like the asynchronous is so important, and you want to put it into giant batches. Because what I found was if you call for both with the input tensor of just one board, and then you call for both again, it actually waits for the first for both to finish before the second one is serviced. So if that was the case, you're not using your GPU almost at all. And at the beginning, I was barely using my GPU like usage, barely using it completely. So I realized that if I can put 64 boards into one, then I actually started using my GPU. So I found out that okay, I just need to make this completely asynchronous, where I can batch combine a bunch of board states together and send it in one go to the GPU to work on. And that's the send to GPU. The create tensor board helper function. I'll go back up for the public functions, but I wanted to talk about this one. Um, so you have a simple board with in size, last move, B turn. And it's important here why I have 4 here, because each one of these encodes a different kind of view of the board. And people think that you just need to give it the board and kind of figure it out. When I did my research on AlphaGo AlphaZero, they had to encode a lot of meta or like extra information about the state of the board into the actual input tensor itself for it to work. And how they did that was here is essentially saying the first order dimension, it only encodes the moves that player 1 has made. You'll see here like 1, if the board is 1, only then do you set it to 1. This is a second order dimension. It only encodes it if it's player 2 that plays it there. Right? It's not equal to 0. This is essentially going to be equal to 2. Because in how I play, it's 1 or 2. But yeah, it's that's so you have a entire 15 by 15 board just to encode the first player moves. The second player moves does not show up in this board at all. Same thing for here. Only the second player moves show up on this second order dimension board. The first player doesn't show up. The third board is actually the last move made. So it's mostly zeros. I should mention torch zeros. It creates a n-dimensional array with everything zeros. But yeah, in here, I just set a single position to 1. Everything else is 0. And that's the third board. And the fourth board is the entire board is either going to be 1 or 0. 1 if it's player 1's move, 0 if it's player 2 move. So all the information that you usually don't think about, it actually has to be encoded into the tensor board, which is why I made an entire helper function to do that for me. Okay, cool. So that covers a lot of nitty gritty stuff. The save model, load model, that's pretty simple. It's just saving and loading to disk. Predict value and predict move and predict both is very simple. All you're doing is you're creating the tensor board and you're giving to the network to forward the value, forward the policy, and then just returning what it comes back. Predict both is very similar. You create tensor board and use the call to forward both, and then you return the policy. And I already talked about predict both async. So that's essentially how you do the playout, the rollouts when you're generating the training data. Once you have the training data, you can come to the train function. In here, you set the network to be in train mode and do a bunch of stuff here. And this isn't really like, it looks really complicated, but all it's doing on a high level is that this training examples DQ can be 1,000, 10,000, maybe even 100,000 lists long. And you can't put all of them into one single tensor and put it to the GPU. There's just not enough VRAM on it for that. So what I found is I need to put it into 64-byte chunks. And all this, most of this here is one, you need to separate out 64-byte chunks, and then you translate it into a torch tensor, and at the end, you feed it into the GPU. One thing here to note is the epoch. Epoch is how many steps you want to make. In neural networks and how it learns is that it's basically a minimization function where it tries to find the minimum of a dip in a invariable equation. If you imagine a 2-variable equation, which is like a parabola or something like that, you have you're at a certain point, right? And you have a slope at that point using calculus. If you know the slope, you kind of know the direction of it down. And if you're taking a small step, you need to take multiple steps to get closer to the minimum. So in that analogy, the learning rate is how big of a step you make, and epoch is how many times you make that step. So for for this example, let's say I have a learning rate of 0.2, I might set the epoch to like 10, right? I'm making 0.2 the slope 10 times. That's not exactly the equation, but that's the idea is the same. The epoch is how many times you wanted to make that step. I think by default I have epoch as 10. So then that's why there's a loop here to do this 10 times. Um, it's not efficient because I create the torch tensor and kind of lose it, but just due to memory limitations, I just wrote it like this. And honestly, memory and speed is not on the system is not that big of a deal. It's usually the VRAM and GPU. While it's training down here, train GPU async and train GPU async. While it's doing that, it's asynchronous and it can go through and calculate the next batch that you can send over. So it's not that slow, honestly. I create the optimizer with the learning rate. The parameters are fed into the optimizer so it knows what kind of layers are within it. And all of this here is just basically translating the stuff that was in the training example into a input tensor, and also creating this, what I like to call the answer key. So the input tensor is the board state that was at a given position, and the value and policy is basically a dumbed down version of what the final answer was. So let's say if player 1 won, the value answer is going to be 1 for every single game, every single board state where player 1 won. And the policy answer is basically um, every single move that was played in that entire game, you just put 1 there for the position that was played, because when due to this chain of moves caused player 1 to win, and you no longer have any kind of values in the other positions of the board. You just have 1 in that one position, and this is what I like to call the answer key. So a lot more finagling to make sure I have 64. The promise here is getting the GPU async training. This promise, I use it to log the loss, which I'll get into later. But yeah, um, all this stuff is just making sure I get into size of batch 64. Once I have a size of 64, I send it to train GPU async, which is down here. I zero grad out the optimizer, and then I calculate the loss. Now, how it calculates the loss is you give it the actual input tensor of the 64 board states, and it outputs out 64 policy tensors and 64 policies and 64 values. And how you calculate that is this is what it thought, and you have an answer key. So you use the answer key and find a difference to what the current GPU thinks it is. You take the power. For the value, you just do this, which is an equation that I found online for AlphaGo AlphaZero. It's quite well documented, so you can find it out. This is the exact way that you're supposed to do the equation. But then you just plus the 2 losses together, and you take the average of that. And this is averaged through all the 64. So you average out the 64 and you put it into one loss tensor. And this loss tensor is one single number to represent how different from the answer key your current predictions are. And the optimizer will try to make this loss tensor as close to 0 as possible with the backwards command, which is a calculus function to walk down the slope. So it finds a slope and it walks down it using the optimizer's type. And then you opt step. I return the loss tensor here, which is what it currently is, and I use it for logging, and that's it. You have trained the GPU in one block. While the GPU was doing that, the system was quickly calculating the next block, trying to get it ready so that when it exits out, loss I get promise get. This is blocking. It waits for it to get. It can feed it to the GPU again. So 64, you keep sending it to 64 byte chunks, not bytes, 64 chunks to the GPU. And that should be it. Yeah, there's no more functions. Cool. So that's how the agent works. I hope whoever looks at this in the future, most likely me, can understand what I was trying to do here. And next video, I'll probably talk about the Monte Carlo rollout algorithm and the trees and nodes that I wrote for that. So see you next time.